Okay, now this is the topic. Previously, we were finished with this crypto arithmetic puzzle or problem. And now this is the topic backtracking, which we have to start. So backtracking is basically an algorithm which is for searching. And especially when you are in a depth first search, and then the tree would be like that. You will start from here and you will go to the next node, and then you will go here. And then you will open up this next node, and then you will go here. Then you will open up this next node, and you will go here. This is the depth first, for this tree. Now, suppose that when you will reach here, or when you will reach here, this is not your goal. This is not your solution. Your goal is maybe here, or this is not the right example. Then suppose that you started from here, according to the depth first search. You started from here and you reached here. And then you want to, and you are assigning these different colors to these nodes. And then you reached here. And here the colors are whatever, 4 colors are displayed, and you reached here. And suppose you don't have any color left for this node, suppose. Or you don't have any value left for this node. Then you will do what? So when you reached at some point where you don't have any value left for these variables, these all nodes are called variables, and you are assigning values to these different variables. So, and suppose at this point you have not left any value for this variable, and the value can be blue, yellow, brown, or green. Okay, if you don't have any value left for this variable, then here your algorithm will halt, or where your algorithm will stop with an error, and your algorithm will not find any solution for this. Then what? Then the problem may be not here. Problem may be at the previous point, or on all the previous points the problem can occur. Then you have to go back. Okay, then you have to go back, and then you have to try a different value for this node if possible. When you will try a different value, then you will have some option open for this variable. This is not exact the map coloring, but I'm trying to give you the idea why we need backtracking. So we need backtracking in searching algorithms whenever we stuck in the search, during the search of the algorithm, whenever we stuck and still the algorithm is not completed yet. So when you stuck, then you will go back to the previous point, and then you will try a different value, and it will open up the options for that next point where you stopped, where your algorithm was stopped. So let's see that. So backtracking is what? It is a search technique for solving problems. Same statement, that you are giving for the other algorithms in the previous CLOs. So it is a search technique for solving problems. And it will solve the problem recursively, because because your algorithm will first go in a normal way from here to here, or and then it will open up this and that. And if you have a problem here, then it will go back. Then it will go back. It will call those different things. Uh, so recursively, it will go to the previous call. So that's why the word is recursively. And it will do what? It will see all the possible options or choices to give us the solution or to provide us the solution. I already talked about that. When you are in depth first search and suppose we have a variable and that variable has no legal value left, then to solve this issue, we will go back. We will go back and then we will try a different value for the previous previous variables. It can be the immediate previous or previous to previous. You have to find that. And then you will go on with the different value for those variables, and it will open up the options for the upcoming or the next nodes. And this backtracking you can use for solving search, for optimal algorithm. Optimal word, optimal, you know that the best possible solution, the algorithm which are giving you the best possible solution, those algorithms are in the category of optimal algorithms. So you can use this backtracking for simply solving search, for optimization, for general planning and gaming problems. Now we are moving toward this algorithm. This is the algorithm for the backtracking. With this, we will run this algorithm over this example. This is the map of Australia. And suppose this is the set given to you where WA is Western Australia, and T is equal to Northern Territory, Q is Queensland, NSW is this, V is this, SA is this, T is this. Suppose this set is given to us, we will follow this set when we will run this algorithm. Nothing else, okay? So backtracking, okay, this is the algorithm backtracking. We are passing some problem into it, and suppose this is our problem, we are passing it to it, and here we are calling recursive backtracking, which is the function given here, and we are passing an empty array or something, you can say an empty statement, and this statement will copy here in this variable, which is assignment, and then the problem CSP the same as it is. This function will return us the solution and the failure. Okay. So initially, now we are from this statement, we are calling this one. And what is the value for assignment? What is the value for the assignment? Empty. Because this empty, we are passing it. And this CSP. Now, here, the value of the assignment is empty. So if here now we have a condition and we are checking if assignment is complete. Assignment is, value of assignment is what? Empty. And here we are checking condition if assignment is complete. Now here complete means when you have the variables, and when you, if you are not understanding variables and values, just remember this topic. What is CSP? It will contain a set of variables, set of domains, which means the set of values, and the set C, which will contain the set of constraints. Constraint means conditions. So I am following these three concepts again and again. So now here, so what is the meaning of this complete? When you are assigning values to given variables, and if you are going to assign, all variables are assigned, and now you are at the last variable, and when you assigned the last value to the last variable, legal assignment, the last assignment is called the complete assignment. After that last, the problem, you can say the assignment is complete. This is the meaning of the complete. And here we are saying, if the assignment is complete, no, we are just beginning. We are now just in the initial stage. It is not the last stage. So assignment is not complete. The condition is false. And if it is a complete, it will return that assignment. But it is not. So I will go to the next statement. And here, select unassigned variables. This is a function which we are calling, but it is not mentioned here. Okay. What this function will do, I will explain. Select unassigned variable. This will select some variable for you and nothing else. Okay. This will do what? It will select some variable which you will use further. It will select some variable from you for you. And here you are passing all the variables of the problem. It means the variables of the problem. And what are those? Here, this is given. This is the set of the variables which is given for this example. And these are the variables var, nt, q, nsw. And then we have that assignment, that our assignment is still empty, and the CSP, the problem itself. So I have explained these, but you don't have to go into details. You only have to just understand that select unassigned variable is what? It will do what? It will give us the variable according to this order, from this set, according to this given order. According to this given order. So initially it will give us what? The first one, var. So the var will be here in this variable. In this variable, now you have the var in the var. Clear? And then we have a for loop for each value in the order domain values. Now we have another function, order domain value, which is not mentioned here. But what it will do, I will explain. For each value in order domain values. What are the values for this example? You are seeing these values from the beginning. From the map of Australia, what are the values? If I will, well, I don't understand. These are the values, red, green, blue, nothing else. These are the values from the start. Here it was mentioned. So for each value in order domain values. So var is what? Var. Assignment is what? Empty. CSP is what? Okay, this is the, we have to color this map. This is the problem. This is the CSP. And order domain values. Those are what values? Red, green, and blue. This is the set of those three values. So for each value, this loop will execute for each value which is available in the set. And what is that set? Red, green, and if I will write here, it will be red, green, and blue. This is the set for the values. And now, initially the assignment is empty. In the figure, you can see the empty assignment by this node. This means empty assignment. And then this loop will execute for each value. So, okay, we are executing it for the first value, red. So for each value, var is what? Var is our var. And assignment is empty. So we are executing this for loop now for the first value, which is R, which is red. And then here we are checking. So now value is red. This is what? This is value. I don't want to write. It is just a wasting of time. And this is what? This is var. Variable. One by one. And now here, for each value, the first value is now, so it means this for loop will execute how many times? 3 times, because we have 3 values here. And okay, our variable is what? Var. Var means this one, Western Australia. And our value is now red. And now we are checking if red is consistent with the assignment. So what it means? It means our assignment is what? Initially, our assignment is empty, huh? And here we are saying that this red is consistent with the assignment given constraints of the CSP. What are the constraints of this problem of this CSP? What are the constraints? We have to assign colors to the neighbors, but each neighbor must have different color. This is the example that we are taking from the start. This is the example that we are taking from the start. But when I explaining and you all are mostly silent, I don't understand why on the simple, this is the simple example. Maybe due to Ramadan, maybe that you are silent, you are still sleeping, huh? So, and you are not giving me any responses. I am an old man than you. You are a young. Young means you all have the full of energy, full of stamina. Everything is in full, huh? But you are sleeping. Anyhow, so if the value is consistent with the assignment given constraints, so what are the constraint of the problem? Neighbors must have different colors. This is the constraint, huh? This is the only constraint. Neighbors must have different colors. And here we have a condition, value is consistent with the assignment. Value means red. So we are going to assign red to this variable var, and then we are checking that this red for this var is okay according to the constraints. So initially, when you are assigning this var is equal to red, you have not assigned any color to any other region or neighbor. So that's why when you are assigning red for the first, it's okay, consistent. Consistent mean okay, no issue. It's okay, it's legal, huh? So when you assigned this value red to this var, is it okay? Is this assignment is okay? Yes, it is okay because you assigned red here, huh? And here you are writing. So this condition is okay. And if condition is okay, add this var is equal to value. Var is equal to what? This is the var. Var is equal to value. Var is equal to red, which means var is equal to red, huh? If you will replace the variables with the values. Var is equal to var and value is equal to red. So then add var is equal to red to assignment. Add this, and here you can see it is added. Y is equal to red into the form of a diagram. It is now added. So now we are here. After this assignment, we are here. We are calling recursive backtracking, which is this function. Huh? We are calling this function with this new assignment and the problem. What is the new assignment? This one, which I ticked with this red. Y is equal to red. This is the new one. Previously it was empty, but now it is this one. Y is equal to red. So recursive backtracking with this assignment, you are calling this function again with these values. Okay. And these things that you are seeing in the diagram, these are on hold. These are on hold. It is not executed yet. It will be executed, but it is like a depth first search. So it is going first in the depth. But here the figure is drawn not fully. The figure is drawn in half, but these values are also displayed. And it is making confusion. But you know that according to this algorithm, so these nodes still the algorithm has to explore. But this one is done. This one is done. Up to this point. Up to this point, this one is done. And this loop must have to execute for these remaining two, and then you can have these two. Otherwise, not. So for the red, it's okay. Oh, and we have called this recursive backtracking again. Okay. And now, what is the assignment? Assignment is this one. If I am, I want to remove. So this is my current assignment, huh? And you are calling this function again with y is equal to red and the problem, and here you are checking assignment is complete, y is equal to red is complete. No, assignment will complete when you will reach at Tasmania and you will assign the colors, and then this loop for Tasmania will be ended. That would be the complete, huh? So anyhow, so here you are calling assignment is complete. No, select unassigned variable. Okay, then I will, previously it was selected this one. Now I will select this one, NT. Now I will select this NT. And now in the var, we have, now in the var, we have what? NT. And there's this loop for each value in the order domain values. Now execute this loop for each, for each of these values again 3 times for the new variable, for the new variable NT, for the new variable NT again 3 times. And initially, and then what? And initially you will check with the red. Again, it's again that red, that red is checked for the war, but for NT you have to check it again. So initially you have to check with the red. So you are taking red value and then you are saying, okay, this, if you will assign NT is equal to red. So previously var is equal to red. Okay. And then here, if you will assign NT is equal to red, NT is equal to red, if you will assign, is it okay? Red, according to the constraint, is it okay? It is not. So it is not. Then you will do what? So this condition is false, and these all statements are under this if. So you will go again to this for loop. And now you will do what? For the second value. And what is that second value? Green. Now you are checking green, because you have to execute this for loop 3 times. So now you are checking with green. So now the value is green. Green is consistent with the assignment. Variable is NT. So if you will give this green to this variable NT, and then is it consistent? Is it okay without issue? So var is equal to red and NT is equal to green. If you will give green here, so now the neighbors have different color. So is it okay? Yes, it is okay or not? Is it? Now it's okay. Now it's okay. Add this NT is equal to green to the assignment. Now take this as an assignment. Add this new thing into the assignment. Okay. Now you can see NT is equal to green here. Previously, var is equal to red. Var is equal to red, which is mentioned here. Okay. Now this is the, now this NT is equal to green, or you can say this whole is the assignment. Actually, this is now here. That y is equal to NT is equal to red is done in the previous step. It is up to you, because we are going logically. So you can consider the whole, or you can consider one by one. But according to this algorithm, it is going one by one. So NT is equal to green. Okay. Now after this statement, now recursive backtracked with this new assignment and the problem, and we are calling this again. And for one, and this loop is not finished yet. This loop is done for 2 values, but one is remaining, which is mentioned here, only for understanding. But you know that var is equal to red and NT is equal to blue is remaining. It is not done yet. Okay. It is not. So that's why it is incomplete. It is remaining. Now we are calling again, and this is our latest assignment. We are calling this algorithm again. Assignment. This is var is equal to red, NT is equal to green is, or you can simply call it NT is equal to green is the assignment, CSP is the problem. And here we are checking this assignment NT is equal to green is complete. Is the last assignment of the problem? No. Condition again false, This condition again false. It is not complete. Complete mean last assignment of the problem. Last and legal. It is not complete. So condition is false, and then select unassigned variable. Okay. Select this next variable. Now Q is our variable, huh? This is, and now that will, Q will go into the var variable. And now we have the for loop. For each value for the order domain values. What are the order domain values? These three. I'm I'm drawing third line, huh? For so this loop again will execute for these three values, red, green, blue. And for first value is now, for the first, the value is now the red. So, and here we are checking that if we will give the value red is to this variable Q, then is it consistent? Then is it consistent if we will give the value red to the Q? So this is R, this is green, and if we will give this Q to R, is it okay? Consistent mean, is it okay? Is it legal? Yes, neighbors have different color, no issue. So the value is okay. Then do what? Add this assignment, add this pair. Q is equal to red to the assignment. And here you can see it is added. Here, var is equal to red and Q is equal to red. It is added. And then you are calling again recursive backtracking. You are calling this again with this assignment. And if you will give green here, that is not okay. And if you will give blue here, so that is mentioned here, but it is not completed yet. Or you can say for red, it's okay, but green and blue are still remaining. But green is constraint wise, it is not legal. Huh? So that's why it is not mentioned, nothing else. Nothing else. If you want to mention three, you can mention three. But you know that the green is already with this neighbor, so green is not possible here. This is what constraint satisfaction problem is doing. If you are following constraint satisfaction, then you are not checking all the conditions. We said this in the previous slide that it is reducing our work, not increasing our work. We have to give different colors to the neighbors. And if I will give green here, that is matching. So don't consider green. Only two options. Only two options. And in this way, you can go on. You can go on like that, and then finally you will reach at a solution at this node. And suppose that at this variable you don't have any color left. Suppose for Q you don't have any color left. Then what will you do? You will go back to this previous, and then you will check, you will assign NT is equal to blue maybe. You will change the option. Suppose so then you will do what? You will, if you don't have any value left for this Q, you will go back to the previous node, and then you will assign different color to this NT. If it is green, green is moving us to a condition where we don't have any value left for the next variable. Then what? We have to change this value. NT is equal to blue. So maybe, so then you will follow this. This would be the path of the solution in the tree. I can draw the whole tree, but I'm sure that you have no idea because you know what is depth first search. So that's why I'm just stopping. You can complete this by yourself. And in this way, it will go on, huh? And it will go on for all the variables. Now I will move you toward these statement. When we will reach here. So suppose this is now the red, this is now the green, then Q, this is now the red, then NSW, now this is, I cannot make it red, so I can, according to the sequence, red, green, blue, I can make it green. And then V, it is red, and then SA, so I cannot make it red because red is here, green is here also, so I can make it only blue. And then T, it is again according to this algorithm, it is red. It is red. So finally, when you will call this assignment with this Tasmania, and then you will say assignment is complete. This Tasmania is assignment is complete. Yes, it is complete. And then it will return that assignment. Then it will exit from the algorithm. This is one condition. When this algorithm will come here, if the value is consistent, when this okay, when this Tasmania, it will return assignment. When this Tasmania is red, when this Tasmania is red, the last assignment, and here you are checking assignment is complete. Yes, it is complete. Return assignment, and you are returning Tasmania with the red. You are returning. So, this call is returning, but previously it was called here. So that Tasmania is equal to red, it will come here, huh? Because you are returning, and that was the call to this function. And that call is now returning the value. That value will come here in the result. It will come or not? You can imagine this tree is a complete tree with the last node Tasmania somewhere, huh? With the last node Tasmania somewhere. And now this call is complete. It will return the value to the previous call, huh? According to the tree. And then you will have the value here, result. And here you are checking result not equal to failure. This Tasmania, that was the last complete assignment. So it was not it was not failure. Condition is true. Then return result. Okay, it will return. So you will have the complete tree, or you can say, or you can have the map assigned with colors. Suppose if you don't have any value left for this Tasmania, which is not possible, but suppose, huh? But suppose you don't have any value left for this red, green, or blue. You don't have any value left for Tasmania. Then what will happen? So 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 one thing is value is consistent, it will not consistent, and then this loop will finish, huh? And then this loop will, you don't have any value. So it will be, this loop will run for red, for then green, for then blue. But it will not find any assignment, huh? It will not find any assignment. And then this loop will be finished, and then you will come here, return failure. Then this call is returning failure. And that failure will also come here. And this failure will also come here at any point. This failure is also, we are receiving here. Maybe this call is giving us failure, huh? That failure will come here in this result. And then we are checking result not equal to failure. Condition false. It is failure. It is failure. So condition, and then you will come here, remove that previous assignment. Remove that previous assignment. So I will remove this Tasmania from the assignment. Remove that. Remove this assignment from the previous. So here we have not assigned any. So what is in the Tasmania? Maybe the previous assignment is Victoria. And whatever the color I have there, for example, red, I will remove that. And the algorithm will go again for the second iteration of the loop, and it will change the color, and it will go again. Huh? This is the idea here. Hopefully, you have the understanding, and this tree is also giving that understanding. We will see that in the next slide. When the time is finishing, huh? 45? Okay. So now the problem is, so this is the backtracking. So again, in words, what is backtracking? Again, in words, what is backtracking? So backtracking, it can occur at in any algorithm, okay? But for easy understanding, we are here giving you the example of depth first search. For easy understanding, you have the example of depth first search. But this backtracking, normally an algorithm, when you stuck in a search, then you have to go back to the previous step. And then you have to, in the previous step, if you have assigned some value, you have to change that value with some other value. You will change that, and then you will again execute the algorithm from that point. And then maybe you will have your solution. Huh? And maybe you will not stuck again on that point. So this going back and changing the options in the previous step, this going back, this is the word backtrack. Huh? This is the word. You have to track the error in the backward direction. In the backward direction. This is what it means. So, how we can improve the backtracking? Now, the question is how we can improve it. So, in the backtracking, if you will see this is one function, select unassigned variable. This is another function, order domain values. This is again constraints. Okay, leave it. Maybe it will be helpful. So, we will focus on these functions. If you will do something good in these functions, then the backtracking algorithm will be improved. So here we are saying that if this function select unassigned variable, here how we were selecting variables according to this order. How we were selecting the variables according to this order. First we selected this, then we selected this, then we selected this, then we selected this, then we selected this. If we can, this order, what you are selecting the variables according to this order which is given in this set. This is called chronological order. This is called chronological order. The order which is given in the set, you are taking according to that. This is called chronological. But if you can change this order by adopting any policy, yeah, then it can happen that you can improve the backtracking. If because the possibility that it will maybe stuck here when the queue is red, it can happen that it will stuck here, and then you are not selecting that, you are selecting some other. So you are jumping over the problem or something like that. So I can explain also something other, but that will come automatically in the next slides. I don't want to say it here. So you can change the order of the variables, and then you can improve the backtracking. Similarly, you can change the selection of the values. You can change the order. In the previous algorithm, we were selecting red first, then green, then blue. You can select maybe blue first, or maybe green first, or something like that. So you can change the value, order of the values, and then maybe you can improve the backtracking algorithm. And then there is another function which is not here in this algorithm. And that function is inference. Inference. Inference normally means to extract something from that existing thing. Huh? Normally, inference means you have to extract something from that existing thing, or you have to conclude something from that existing thing, whatever you want to say. Infer, maybe the Arabic word, I don't know, the Arabic word is akhaz. Akhaz, alif, khe, and then zaya. We call it zay, you call it da. So actually, I don't know. In Arabic, we have this letter. You call it da or whatever they. We have this letter also in Arabic. I don't think so. We have two, huh? So in Urdu, we call it here ze, and then here zal. Okay, in Urdu. So just different pronunciation. So anyhow, this is not the topic here. Okay, but just for information, huh? Inference. Inference is you have to extract something, from some existing thing. So this function is not available here, but you can also use this function to improve the backtracking. And the new version of your textbook, you will find this method there, okay, inference that is available there. What is that? This inference, when you will run some algorithm, and if there is a chance that your algorithm will stuck at some point when assigning values to the variables in future, your algorithm is at point X and the point Z is in future, huh? This inference function will do what? It will always keep an eye in future values. The algorithm is at point X, but it will keep an eye in future movements, huh? And if there is a chance of occurring an error in upcoming or future events, then this function will detect that error and it will show you that this is not the right way in which you are going, okay? You this is not the right way. It before before your algorithm will stuck there, it will inform you that the failure is coming in the upcoming assignments. So you can also use this inference function to improve the backtracking. And now the four things about the backtracking algorithm. The four things: it is complete or not, optimal or not, what is the time, what is the space, the four things that you are discussing from the previous CEOs. So as backtracking is following DFS, depth first search, then you have to apply all the properties of the depth first search on this backtracking. And if you remember, then the depth first search was not complete due to repetition, okay, due to repetition. And for finite spaces, when you don't have any repetition, then it is complete, okay, then it is complete. Optimal, if something is not complete, then optimality is also gone. So no optimal, but you can optimize it through some heuristic by introducing some heuristic function. You know that what is heuristic function from that previous CLO. You can introduce this optimality by introducing the concept of constraint satisfaction problem. When you will introduce constraint satisfaction problem, you will remove repetition, okay? The things which are already visited, you will not visit them again. For example, the color that you have already assigned to the neighbor, you will not assign it again. Similarly, graph search, and you know what is the definition of graph search. The things which are already visited, you will not visit them again. So that is graph search. So you can improve the optimality of this algorithm by using these three different concepts. Whatever the time complexity of the depth first search is, that is the same for the backtracking. Order of b raised power m. M is the maximum depth of the search tree. Maximum depth. If it is on the, it will go up to the maximum depth. Space complexity, you are multiplying this m with the maximum depth. You are not taking it as an exponent or power, you are simply multiplying. If it is on the first first branch, you can say. Okay, that is the same. And now backtracking n queens problem. We already have seen n queens, 8 queens, where you have to place a queen in each column or in cells, in the different cells. 8 queens. What were the problem? You have to place 8 queens on the chessboard, none attacked, huh? That was the condition. The constraint was none attacked. So now that was the n queen problem. So now you can use this backtracking method to solve that problem also. You can use this backtracking method to solve this n queen problem. You can use this algorithm. And backtracking is what? Okay, DFS. So you can use this depth first search based backtracking algorithm for finding the solution for that. This is just a theoretical algorithm written here. What is that? Initialization. You will have a empty chessboard initially, empty chessboard. Then the step two, you can place the nth queen in the nth column. If the first queen, then you have to place it in the first column. If the second queen, you have to place it in the second column. Third queen, third column. Fourth queen, fourth column, and so on. This is that step. And check constraints. Now you have to check the condition. What is the condition? Okay, for example, you have placed first queen in the first column. Okay, then you have to verify that the current placement that you have placed this first queen there, and this placement, you have to check that this placement that you have done is legal or valid or not. Consistent assignment. Consistent assignment. Here, consistent assignment. Where it was, where like that, this condition. Check constraint. So we have placed the first queen in the first column. This is we done. And now we have to check that this placement that we have done is valid or not. What is the mean of validity? Meaning is you have to check the constraint. You have to check the conditions. What were those conditions? That the no other queen is in the same row, column, or diagonal. So for example, you have placed this queen here in the first column. And then you have to check no in the row, no in the diagonal, no other queen. No other queen in the row, diagonal, or column. This is first you have to check in this step. And then backtrack. So when you have done that, if it is valid, then no issue. But if it is invalid, if there is some other queen here maybe, huh? Suppose if there is some other queen in the row or column or diagonal, then it means that this is not the right position. You have to, and your algorithm is now stuck, huh? Your algorithm is now stuck. Your algorithm is not finding the solution. Then you have to do what? So if the placement is invalid, so now the current queen that you have placed, if it is invalid, then what? Backtrack to the previous column. Go back to the previous column, not this one. The previous column. Here we don't have the column, but suppose if I am placing something here, then I will go to this previous column. Okay, this is what it means. Backtrack to the previous column. Go back to the previous column and try some other position for that queen. And try placing the queen in the next row, in the next cell. If the queen is here previously, you have to move it here on the next. Or you have to move it here. If it is still not, then you have to move. You can say you have to move it next. You have to change the position. This is what the step number 4 is. And then recursive call. What is step number 5? So when you done this, the first queen in the first column or the second queen in the second, at any position, whatever the placement is, if the placement is valid, no issue. Huh? If the whatever the placement, for example, here you placed it, you checked row, column, diagonal, this is valid. Huh? If it is valid, move to the next column. Then move to the next column and think for the next queen. Go, then this is now you are allowing your algorithm to do the next job. Huh? If valid, go to the next column, move to the next column, and recursively repeat step 2 to 4. So these steps 2 to 4, and do the things again from step 2 to 4. This is what it means. And repeat the things from step 2 to 4. Okay, then you will go back again and place the second queen in the second column. Check it is valid. Okay. If not, then this backtrack will execute, and then you will come again here. Then you will assign the third queen, third column. And in this way, you will go on. Up to which point? Up to step number 6. If all n queens are placed successfully, for example, like that, here in this, you have all the queens placed successfully without violating any constraint, then you have a solution. So this, the whole process is in between these dots, huh? I have placed this thing for you. It is initially it is empty. And then here we are placing this queue, the first queen in the first column. And then after that, this is then we are placing the second queen in the first column, and then you are checking it is not okay. So then, okay, this is not a good option, crossed. And then you are moving, you are moving this to the next. Is it okay? It is valid or not? It is still in the diagonal, so this is not an okay. So and then you are moving this in the third position. Is it okay? In the row, diagonal, and in the row, column, and diagonal. Now this position is okay. Huh? If this position is okay, then you are moving next to for the third queen. And third queen, it is in contradiction. Huh? So then this is not the right choice. And then move this to the next. Okay, move here. But it is here in the contradiction, so that is not the solution. Then move this to the next. And it is again in the row, that is not right. And then move it into the next, and it is again in the diagonal, so it is not right. So now your algorithm is stuck. Now the backtracking will work, okay? Now the backtracking will work. Your algorithm will go back. Your algorithm will go back. But here, the second was assigned, and we were checking the third one here in these steps. But this third is finished, so we went back to this, and then here we will move this to the next cell, huh? According to the algorithm.
Solution for the current step, but it's a bad solution for the next step. So we have to change the condition.
Yes. So according to the backtrack, I'm going according to that previous algorithm. Okay, this algorithm that you have seen here, or this algorithm that you have seen here, I am following that algorithm. Okay? I'm not following anything else. Okay, I am following depth first search, and I am assigning values. So I will go back and I will move this second queen to the next row. Okay, but I cannot do this here. So here you will go back, and then this is according to depth first search. This is here. I moved this point to this queen to last row. This is according to the depth first. Now we are checking again. So now we will check for the third queen. Now second queen is now in place. It is no row, no column, no diagonal. And now we will check for the third. Third is here, not okay, crossed. Third moving next. Is it okay? Yes, not row clear, column clear, diagonal clear, and also with this one. It is clear. So now what are the, now I will check for the fourth one. And here, if you will place fourth here, no contradiction, false. And if you will move this to the next, no contradiction, false. If you will move here, this is contradiction with that, false. If you will move here, no contradiction, false. Algorithm again stuck. You will go back. Then what? You will go back. You have to move this queen somewhere in the next. And here, okay, you will go back, and here, this is the next position. You moved it here, but this is not okay. So that is, again, algorithm is stuck. You will move back here, and then you will also check to move this here, which is also wrong. So then what? You will move back here, and then you will move back here. Now this is at the last, and no any position left. Okay. So then what? You will again move back to the previous column. So go here. And here in the previous column, it was the first position. Okay. And then you move this first queen in the next. And in this way, you will keep on doing that like that. And finally, you will find a solution here. This is easy. Okay. This is only the size wise a lengthy tree, but it's easy in understanding if you will go like that. I will start from here next, inshallah.